Hi everyone and welcome to the 4th annual HashiTalks. My name is Andrei Buzoianu and alongside Elif Samedin we'll be presenting Take Control of Your Data by integrating HashiCorp Vault. First of all, I'd like to thank the organizers for inviting us here today. Now this should only last about 25 minutes. As for introductions, Elif is a senior DevOps automation engineer with experience in infrastructure optimization and management. A Red Hat certified architect in infrastructure level 2. She is well versed in using Terraform, Packer, and Vault. Also an advocate for continuous learning, open source communities, and technical innovation. Let me introduce myself as well. I am a senior solution architect with a focus on designing and implementation of complex systems at scale. I have more than 20 years in IT and extensive experience in system and network administration, automation, security, site reliability engineering, and CI/CD pipelines. Now, today's topic is of a particular interest to those of you who have been in data loss situations due to common events such as system crashes or unavailability, or have often needed to transfer data between systems for migration projects or simply data restoration and data liberation. Basically, I'd say that's all of us. So yes, we are talking about data backups and more. Systems we manage nowadays use data across on-premises and cloud locations, and we often find ourselves demystifying the belief that simply entrusting our data to a reputable software as a service provider absolves us of the accountability towards protecting that particular data. Granted, in some cases it would be enough, but in others it won't even be possible to use a managed service. Suppose you wanted to address the issue. How would you? Well, we thought about it and decided we should start with a backup strategy, with a set of best practices that can be leveraged to implement a multiple-layer solution which will mitigate the risk and ease operations. Thus, we created an internal guide to manage the approach, or a curated list of practices, if you may. We ended up with the following nice diagram on the drawing board. So, what are the key points? The security practices constantly evolve to mitigate new risks as well as environments we work on. Thus, we needed a very simple yet flexible strategy to secure backups. We should include disaster recovery and business continuity plans in our strategy. Simple yet effective decisions like having multiple targets for backup storage. We should integrate access control lists and leverage existing tools if possible. We should automate the process of backup and restore. Use tools such as Ansible to configure, manage, and govern backup activity across supported resources. This is very important. Encrypt data in transit and at rest. Here comes Vault to the rescue. By the way, thank you HashiCorp for creating Vault. Implement backup monitoring and alerting. Backups can fail and sequentially may have an unforeseen impact on your systems or business. Always test the recovery process. If data stored as backup can't be successfully restored when required, then our strategy is not that effective. Audit and compliance. Validate whether the backup strategy is included and compliant with your security program, business requirements, or in the scope of compliance programs such as HIPAA, GDPR, or PCI DSS. Design an audit process as part of an overall plan for continuous improvement of your system. We talked about automation as a key point in our strategy. Automation is the way to provide high availability when managing the size and complexity of modern networks. Let me introduce you to the most relevant building blocks for our solution. Restic, Ansible, and of course, Vault. We chose to demonstrate how they can work together in a Kubernetes environment. Restic is a modern backup program that can backup your files to many different storage types, including self-hosted and online services. All data stored by the Restic in its repositories is encrypted. Ansible is an open source IT automation engine that can automate many IT processes. Encryption of data in transit and at rest. This is possible to do to Vault. Doesn't really need an introduction, but here it goes. A secret management tool. It secures, stores, and tightly controls access to passwords in our case. Alright, let's dive right in. I now invite Elif to show us a demo.
Thank you for the introduction, Andrei. Hi everyone, I'm Elif. Today, we are going to demonstrate how to create backups in the Kubernetes ecosystem using Restic and by leveraging Vault's capability to encrypt data during transit and at rest. Our lab environment for this demonstration consists of a Kubernetes cluster of 4 nodes named CL1 to CL4. Firstly, I'll create a host path persistent volume, which uses a directory on the second node in the cluster, CL2, in order to emulate network-attached storage. The configuration file specifies that the volume is at /mnt/data on the cluster's node. It also specifies a size of 1 GB and an access mode of read-write once. This means the volume can be mounted as read-write by a single node. Next, I'll create a persistent volume claim, which will be used by pods to request physical storage. The persistent volume claim is now in place. Let's go on and create the Nginx deployment, whose configuration file also specifies the previously created persistent volume claim. It has 3 replicas and exposes port 80. Let's wait a bit until all the pods are up and running. The 3 replicas have now the status running. Let's expose the deployment by creating a service of type node port. As the service is in place, let's check that the content is properly served in the browser. And voila! HashiTalks 2022. Next, we want to ensure that our data is backed up in a secure manner. This is the very moment when Vault and Restic come into discussion. The Restic init job has 2 components, an init container, which runs the Vault agent, and the Restic container. The Vault agent is responsible for retrieving the password in order to secure the backup and write this to a shared volume. Restic initializes the remote repository. But what is a repository? A repository defines where our backups will be saved. This is passed as an environment variable. Restic reads the password from the file which was previously written by the Vault agent. Let's now create a job. The job is in place. Let's check the container logs in order to ensure that the repository has been successfully initialized. And indeed, there it is. Let's now create a cron job, which will perform backups periodically on a given schedule. Similarly to the previous job, the cron job has an init container running the Vault agent and the Restic container to do the heavy lifting of backing up our data. This will run every 5 minutes. Let's confirm that the cron job has been created. And indeed, there it is. Well, as we wait 5 minutes until the first backup is completed, let's dive into the Vault UI and Vault agent. I have enabled the Restic KV secrets engine, which contains our sensitive data, the password to encrypt the backup, and the SSH private key used to connect to the backup server. I have also created a policy which allows read-only access to the previously created secrets engine. The next natural step is to discuss about authentication methods. I have also enabled the Kubernetes authentication method with the default path and created a role named Restic that maps the Vault auth Kubernetes service account to Vault policies and default token TTL. By default, secrets in Kubernetes are stored in plain text in the etcd. However, depending on the circumstances, this may pose a significant risk because anyone having cluster administration privileges will be able to read all the secrets in the cluster. This is the very motivation of integrating the Vault agent. But what is the Vault agent? The agent is a client daemon that behaves as a Vault client, running alongside other applications. It can automatically authenticate to Vault and manage the token renewal process for locally retrieved dynamic secrets. This is why the application does not need to implement the Vault API in order to authenticate with Vault. Moreover, Vault agent templates allow Vault secrets to be rendered to files using console template markup. The application simply accesses the rendered output file. The config map Vault agent config nginx creates a Vault agent configuration file. Let's look into it a bit. As you can see, the Vault agent auto-auth block is configured to use the Kubernetes authentication method. The sync block specifies where to write tokens, and the template blocks create templated files which retrieve the Restic password and the private SSH key used to connect to the backup server. The Vault agent injector intercepts both create and update events in Kubernetes. The controller parses the event and looks for metadata annotation. In case these are found, the controller alerts the pod specification based on other annotations present. There are two types of Vault agent containers that can be injected. The init container, as we have previously seen, prepopulates the shared memory volume with the requested secrets prior to the other container starting. On the opposite, the sidecar container authenticates and renders the secrets to the same location as the pod runs. The Vault agent simplifies the Zero Trust adoption journey by reducing both the effort and time needed by application teams to integrate with the Vault. Applications can now easily integrate with the agent, which in turn handles authentication into Vault along with the fetching, rendering, and lifecycle management of application secrets, and the caching of these secrets to reduce the load on the Vault cluster. Well, I think it's about time to check that we have a backup in place. 5 minutes should have passed by now. Let's check it out. And indeed, there are more than 5 minutes past. Let's check the pods. And there it is. There is a pod starting with Restic backup. And the container logs show that indeed we have a snapshot in place containing 2 files and a directory. An additional validation of this would be to run the Restic list job, which similarly to the previous ones runs the Vault agent and the Restic container. The Restic container will only list the snapshots available in the repository. And we have a pod whose name starts with Restic list. And let's now check the logs of the pod. And we see the timestamp when the container was created, and as expected, we have a snapshot in place. Oh, I think that I have accidentally deleted the Nginx deployment. No Nginx pods are running now, and obviously the content is no longer served. Luckily, we are able to restore our data. Let's see how backup restore works. As we have mentioned, we should integrate access control lists and leverage existing tools if possible. Ansible communicates with remote machines over SSH. Restic backs up data via SFTP. In order to do so, we must first set up a server with SSH and let it know our public key. Thus, the same access control lists in place for controlling who can execute commands against remote nodes can be used to control who can manage backup and restore. The backup restore role is responsible for restoring an existing snapshot, either locally, this is the control node in Ansible terms, or on any other server which is managed with Ansible. This is the managed node. A managed node could be the server whose snapshot we aim to restore, or a dedicated backup server, or even a new server which is not part of the current setup. When dealing with containers, the managed node could simply be the node containing our volumes data. The latter is particularly useful when you need to bring a node back to a certain state, as saved using Restic. As I was saying, we can restore a backup either locally or on the managed node. We can also restrict the restore to a subset of files in the snapshot. There are several variables which we can use in order to control how the restore is managed. For our demonstration, we are going to pass command line arguments to the playbook. For example, onLocalHost is a boolean which determines whether the restore is performed on localhost or not. The source server specifies the server whose snapshot is to be restored, the backup name, as it is already suggested, specifies the name of the backup. The backup server specifies who the backup server is. The restore directory specifies where the data is to be restored. Snapshot, which is optional, specifies the snapshot ID to be restored. In case this is submitted, and by that I mean the string is empty, the variable will fall back to restoring the latest available snapshot. Well, a picture is worth 1,000 words. The diagram describes the process of restoring a certain backup to a designated node using Ansible. And now, let's recover our data from backup. By the end of the execution of the playbook, we should have the same index we have seen previously served by the Nginx deployment restored on a certain directory on localhost. Let's wait a bit and confirm this is indeed so. The playbook has completed, and the file should now be available in TMP. And welcome again to HashiTalks 2022. To sum up what we have seen so far, what we have described here is an end-to-end encrypted backup and recovery solution leveraging Vault capabilities. This is a self-managed approach which will work in a hybrid environment. In our opinion, this is a good choice in case you are looking for an effective and easy-to-use solution. This brings us to the end of this presentation. Thank you. All related configuration and code files are available in GitHub. The URL is available at the bottom of the page. I hope you found this presentation useful and will be happy to answer any questions.